Welcome to another edition of Physics Equations. Today we'll be introducing the new equation d equals 1/2 at squared plus the quantity initial velocity times time. This equation has four variables in it, d, a, t, and vi, although t does appear twice. Make sure that you know before we go on that the d is the distance traveled only during the acceleration, the a is the rate of the acceleration, the vi is the initial velocity, and of course the t stands for the time. Now, before we learn about where this equation comes from, let's learn something new about velocity-time graphs, specifically as it goes to area. This is the graph of an object that you can see was stopped during this time, and then had a speed during this time, and then stopped again during this time. It's this area here that we're interested in. That area tells us something about the object's motion. Now, if we were to consider the meaning of this speed right here, well, that would be the speed that object held during the time it was moving. And that speed, since it's constant, would be the object's average velocity. Now, the time that object had that velocity is only the time where the graph is off of 0. But if we were to find that area by multiplying v average times t, what we'd be doing is finding our old friend, the equation d equals v average times t. What we just learned from that then is that the area that's bound by a velocity time graph, the area shaded in pink above, is the distance traveled by the object whose motion is represented on the graph. Now, we happen to do this with a rectangle because finding the area of a rectangle is simple. But that statement is true for no matter what the shape of the graph. So even if an object is accelerating, the area underneath the velocity time graph is still the distance traveled by the object. So let's apply the same logic to that kind of motion on the next slide. Here we have an object who starts with 0 speed. You can tell it starts with 0 speed because at the beginning of the graph, the vi is 0. And it accelerates to some speed because at the end of the graph you can tell the vf is not 0. Now, in order to find the area under the graph, if we took vf times t, so that would be too much area. vf times t would be that much area, and it didn't go that far. What we need to do is find half of that. Now, really, since vi is 0, the vertical part of this graph is actually vf minus vi, which is also equal to at. Remember that vf minus vi over t is a. So if we were to multiply by t on both sides, then vf minus vi, which is that much of the y-axis on this graph, is equal to at. So at times t, again, would be that whole area, which is too much. We really only want the half that's still pink, the half that's not blocked out by the black triangle I just blocked in. Well, that's exactly half of the old rectangle. That leads us to doing this equation, half at squared. Now that comes from multiplying at times t. That finds us the outline of that rectangle. And then, let's make that smaller. And then cutting it in half so we only find the part that our original VT graph actually covered. Now, if VI is not 0, the graph of motion might look like this. And to find the area underneath that graph, remember, this whole process depends on you understanding that the area underneath a velocity time graph is the distance traveled by the object. The area under this one would probably be easiest to find by finding this triangle's worth of area. And if you look carefully, you recognize it's the same as finding the triangle on the previous page. We ended up multiplying at times t and then cutting it in half because otherwise we'd be finding this whole rectangle. So we get half at squared, but this time, Since the object started with a VI that's not 0, the object would also cover this area. Finding the area of a rectangle is simply multiplying the y-axis, which in this case is the original speed, times the time. So we end up deriving the equation that we showed you to start. D equals 1/2 AT squared plus VI times T. Now that equation is useful anytime you know 3 of those 4 things and want to find the one you don't know. So let's take a look at a couple of things we need to be careful of with that equation and then do an example problem. All right, first I want to warn you that you can rearrange this equation, but there's one of them that is a little bit more difficult. Let's rearrange it for something pretty simple first, the acceleration. So if you're looking for the acceleration, because you've got 2 terms here, VIT and 1/2 AT squared, and a is only in one of them, the first thing you'd need to do is subtract the initial speed times the time from both sides. Then you'd have d minus VIT equals 1/2 AT squared. To solve for a then, you'd need to multiply by 2 but divide by t squared. And when you do this, the 1/2 and the multiplying by 2 cancel, and multiplying and dividing by t squared cancel, but we have to do the same thing to the other side. So 2 times the quantity d minus VIT over the quantity t squared solves for an acceleration if you know the distance traveled, the original speed, and how long it took. Now, the one value that is more difficult to rearrange for is time. Since time is in 2 places in the original equation, if you want to solve for time, you'll have to set the equation equal to 0 and use the quadratic formula. If you're uncomfortable with that process, there are almost always other ways to solve for something else, like VF, and then solve for time. You'll just have to do the problem in 2 steps if you don't want to rearrange this equation for time. Now, rearranging this equation when VI is 0 is actually much simpler, and in that case you can rearrange for time. If VI is 0, well, 0 times, doesn't matter how long it takes, 0 times t is just going to be 0, and if you add 0, well, you're not adding anything. You're going to end up with simply d equals 1/2 AT squared. To rearrange that, for instance, for time, if we wanted to find time, we'd have to divide by 1/2 of a, which is the same as multiplying by 2 and dividing by a. That gives us on the other side 2d over a. That would be equal to t squared. Since what we're looking for is squared, we need to separate everything else off, and then you could square root that entire quantity. Because the square root of t squared is just t, that means the square root of 2 times the distance over the acceleration. Make sure to do everything in the parentheses before square rooting would find you t. Now be careful, remember to do that. We started out with VI as 0. This equation will only work if the original speed of the object is in fact 0. Now, be careful with the units here. Mixed time units will not work out in this equation. Let me give you an example of what I mean by that. If we put in miles per hour per second for the acceleration, no matter what time the acceleration occurred in, if it's seconds, because the equation asks you to square the seconds, it would end up being seconds times seconds. When you go to multiply then 1/2 times a times t squared, one of the seconds will cancel, but the others will leave you no cancellation. You don't have a unit agreement, so you'll get a unit at the end that doesn't make any sense, and you'll get the problem wrong. A better strategy would be to convert to the metric system. If you used meters per second, and then used the time in seconds, and since again the equation calls for you to square the time, it would be seconds times second, then you're dividing by and multiplying by seconds twice, but all of it cancels out to meters. Now make sure that the VIT part also has the same distance unit. So if the VIT part were meters per second for speed and the time were in seconds, when you multiply VI times t, the times would cancel, you'd be left with a distance in meters, and these could be added. If you had left the VIT in miles per hour and had the time in seconds, you can see that you'll get no cancellation. If you converted the time, instead of seconds, you used hours, the hours would cancel when you multiplied it by miles per hour. But if you did this part in the metric system, you'd have meters plus miles per hour, or excuse me, plus miles. Meters and miles can't be added. So I think you can see that the units here are a major concern. You must make sure that you have unit agreement. All of your distances in the acceleration and VI must have the same unit. So either all feet, all meters, or all miles. And the times in every one of these variables, the acceleration has time units in it, the time is of course a time, and the VI has a time unit. All the time units must match. If they don't match, the equation won't work. All right, let's take a look then at what you do in that situation. So here's an example problem. A hurried driver enters the on-ramp to the freeway traveling 25 miles per hour. His car can gain speed at a rate of 5.3 miles per hour per second. 7.6 seconds later, he merges with traffic. How far does he travel while entering the freeway? We'd likely identify the givens as VI is 25 miles an hour, A is 5.3 miles per hour per second, and the time is 7.6 seconds. You'd be right to pick out the equation D equals 1/2 AT squared plus VIT. But before you started, in order to get unit agreement, you'd need to change the 25 miles per hour. If you multiplied that by 1,609.344 meters per 1 mile, and then by 1 hour for every 3,600 seconds, you'd get a speed in meters per second. And if you converted the 5.3 miles per hour per second by using the exact same conversion factors as you did above, you would find that you would get an acceleration in meters per second per second. Now once you have those two, then you could plug in this VI in meters per second here, and the acceleration that you have here in meters per second, that could be plugged in here, and your times, both of them, could be the 7.6 seconds. Once you have unit agreement, it's a simple matter of plugging in the numbers and calculating out to the distance. Now, if you have an equation where you have unit agreement, as you do here, you can see the same hurried driver realizes the English system of measurements is annoying, so he buys a new speedometer that measures in meters per second. As he's making his way at 28 meters per second, a deer suddenly jumps onto the road. He hates deer. We don't know why. So he speeds up at a rate of 2.37 meters per second for 3.86 seconds before narrowly missing the fleeing deer. How far in front of the car was the deer when it jumped out onto the road? Well, VI is 28 meters per second. The acceleration is 2.37 meters per second. The time is 3.86 seconds. So you notice that we've got unit agreement. The distance unit in the VI and the distance unit in the acceleration are both meters. The time is in seconds, and the time within the acceleration is both seconds, and the time within the VI is also seconds. In this case, we could simply plug in the values into 1/2 AT squared plus VIT and get the answer. Be careful and analyze the units in your givens before you go plugging and chugging. Now, before you go on to solve all the other problems dealing with this equation, what's left to do would be to rearrange this equation for all the variables other than D. You can rearrange it for A, you can rearrange it for VI, and you can rearrange it for T. Remember that rearranging it for T you probably wouldn't do if VI is not 0, unless you are comfortable with the quadratic formula. Good luck using D equals 1/2 AT squared plus VIT. We'll see you in physics.